All right, we want to start part 3 by looking at SQL data types. Now, SQL databases support numerous data types of all different kinds of formats. For instance, we can support numeric data. So that's single precision, double precision, floating point data, integer data, and there are operations that we can perform with that, your basic math operations, lots of different ones. It also supports Boolean operations. So these are true, false types of things. So it can evaluate something as being true or false and then support that as a field or a record and then create a query based on that. It also supports character fields, so fixed length characters, varying length characters, and those character data types that it supports have their own operations that you can perform. Similar for binary objects, we can actually store binary objects inside a SQL database. Do you realize you could actually stuff, if you wanted, a JPEG inside an SQL database? So there's lots of different ways that you can work with that kind of data. Also, date and time. This is something you might not see as much in some standard GIS packages. When I say date, I mean an actual date. So my birthday was November 22nd. That normally is stored as character, 1/1/2/2, and then the year. Those are just strings. What we mean by storing a date field and a time field is we know dates that come after November 22nd, dates that come before it. We also know how many days or weeks it's been since a particular date. Time is also important too. When you get GPS units, we can bring in data that has time sequences in there, and we can perform operations on those time sequences. Let me skip down to the bottom one, monetary. So we can handle things like wands and yens and dollars and pounds and so on. So SQL data types are designed for that. It would make sense, right? When you think about all these reservation systems and billing systems that are designed and inside inside a traditional database like Postgres or Oracle or SQL Server. So naturally, they're supporting monetary data types. And then the one that we're really here for the most part, is looking at geometry types. So SQL databases and Postgres in particular stores geometry and geography, which are lat-long based data types. And again, it's just like an integer, just like a floating point, a geometry is its own type. Now, Postgres supports the Open Geospatial Consortium format, OGC. And again, another beauty of this is an open format. There are also other vendor-specific formats that are stored. So, for instance, SQL Server and Oracle have their own formats. But what's also interesting is SQL Server and Oracle also support the Open Geospatial Consortium standard for spatial data object. So let's look first at numeric operations. So numeric operations allow users to perform math-based functions like addition and subtraction, division, multiplication, exponents, all kinds of different things, that modulus operations. They also allow us to perform statistical and other mathematical functions you would typically find in a spreadsheet. And in fact, they operate a lot like a spreadsheet. So let's look at a couple of numeric operations. Let me just copy this. And we'll come in here. So before we do that, just again say select star from TC parcel, right? And that star says, let's select everything. So here are all of our records that get selected, 35,670 rows. Now, what I can also do is select, and we've got a couple of different variables. Let's go through here as we work through. As I scroll through the data, you see I have two fields here. One is called land, one is called ASMT. This is the total assessment for the property. Land is the value of the land. So there are also structures on our land, and basically if we take the total assessment of the property and subtract the land value, we'll get, in fact, the structure value. So let's run this. So I'm going to select the assessment minus the land, and I'm going to call, let's keep it as lowercase, struct value. And also the parcel key. We'll bring that in. And now it's done. So now what I have is the structure value and the parcel key. I can also say select ASMT, land, comma, and let's run that. So now I have all of those. The other thing that we can do is, let me just put these colons in here. We're going to do this a lot. Let's say numeric, colon, colon, and then money. Numeric, colon, colon, money. Now what this is doing, this double colon, is basically telling Postgres, I want you to change the actual data format on the fly. So let's go numeric, colon, colon, money. Let's run this. So now we have these as actual monetary values that you can see. And then the next thing I'm going to do is, let's just type in geom. So now I have the geometry as well as the assessment value, the land value, and everything else. So let's just copy this, and I'm going to bring this back into Postgres. And let's go to the DB manager. So now, again, one of the things that we can do is we can clean this up a little bit, right? So it doesn't matter where you have carriage returns. So let's execute that. And then what I want to do is click my update button. Now, by the way, if you don't have the query results in here from previous things, all you would have to do is add a new layer, or in this case, if you already have it up but you don't have your window open, you can right click and then go to the update on there. So you can see here it says update SQL layer. Now I just ran that, so let me run a query or run the info tool. We click on this and you can see I've got my assessment value, my land value, and my structure value. And the structure value is actually a function of the assessment and the land. Now maybe you're looking at this and saying that's kind of cool, but it's not mind-blowing. Actually, think about this. How would we do this in a classic GIS? If I wanted to get the structure value, which is the mathematical operation of subtracting the assessment value from the land, think about that. Typically what we'd have to do is add another column, meaning we're kind of polluting our database, and then we perform a calculation. What we're doing here, which I think is really slick, and I hope you kind of got the idea about this, is we're performing the mathematical operation on the fly right in the query. But secondly, by bringing the geometry in, I've created a virtualized reality of what the data is, or what the result of that query is. So this is, again, we can select on a whole bunch of these. This is the airport, so that's why you can see it's worth $21 million. And at least in terms of the structure value, because of all the runway and the buildings and everything else. But this is no longer having to create a new type of a layer and write it out to the disk. This is just a query in memory that is virtually shown inside of QGIS. And again, if we hover over this, you can see what the actual query is inside of the little call-out box. Well, for no other reason, I'm just going to use a division term. Right, so we'll come back in here again, and I can just say I want to divide the assessment by the land where the land is greater than 0. And there's our value. So this gives me, and might want to call that percent struct, right? So what percentage of the value of the property is the structure? And again, this is being formulated on the fly. And again, I can come and do the same thing. Let's collect geometry or geom, comma, and I'm not going to bother doing the numeric types. So that's done. And we can come back into the DB manager, select all, paste, and then let's run this again. We can execute it, and then we can update our data. Now what's important here is now I have for every one of these value, I know the percent structure value. Now if I wanted to create a map of this, I can then go into properties, and I can go into symbology. Let's create a categorized, and let's take our percent structure. We'll classify that. Actually, let's do graduated. I'm sorry. And let's do percent structure. There we go. We can make these, yeah, we'll make it red. That's fine. Actually, let's make it more green so it looks like money. Hit apply. And then let's classify with equal intervals. And then you can start to see which ones have greater values for their percentages. Here I just went in and did equal count. We'll classify that, hit apply. And then you can see those ones that have a higher proportion, right? The only reason I'm showing you this is to let you realize that this query that we just wrote can be revisualized and reapplied. Other things we can do here, let's look at the average. Copy that, and we'll go into PGAdmin. So I'm going to say select the average assessment from TC Parcel. That is the average, and then again I can say numeric and then money. So this is the average value of all the properties in Tompkins County. Now I can also put in a where clause, so where prop class is equal to 210. Now that's the single family residential properties. We're going to be revisiting this a lot. And actually the prop class field, I'm sorry, does not have the numeric values. It has the actual types of classification. So this is residential. So now the average residential property in Tompkins County is $221,000. I can change this to commercial, and this is the average commercial value, which is $963,000. We're going to get into more sophisticated things later using group by commands, but at least this will show you the idea that we're performing a function that you would have seen in something like Excel. So finally, let's look at this last one. And I'm just going to copy this, and then we'll talk about it in here. What I really like, again, is both the database administrator in QGIS and PGAdmin highlight our text so we can see what are actual functions. So here I'm getting the average assessment. I'm calling that AVG assessment. I'm getting the standard deviation of the assessment and calling that standard deviation. And I'm getting the sum. And then I'm dividing the standard deviation by the average. I'm calling that as CV. Let's run this. And here we go. And again, we can do this. We can make this numeric. And then money. I'm not going to do it for all of them. But you can see now we have a dollar figure. All right. Just again, mathematical operations like standard deviation and summation. But this, I think, is an important one. Here we're looking at the division between the standard deviation and the average value. And I'm calling that CV. That's actually the coefficient of variation. And it's actually a measure, 2 dashes like this will let me comment things. It's actually a measure of how much variability we have, or how much our standard deviation is in proportion to the average value. So you can imagine the proportion of standard deviation of our shoe sizes compared to our average shoe size as a group is much smaller in terms of compared to, say, the standard deviation of our home values or of our weight, because we have lots of more variation. So in this case, I would almost call this a measure of volatility. So that's sort of interesting on its own. And you know what I'm going to do? I am actually going to make one change. I'm going to jump ahead a little bit, but I'm using something called the group by command, which we'll talk about later. But what I've done is I've added two different things, prop class and group by the prop class. These are all aggregate clauses, average and standard deviation, and this calculation as well. So what I'm going to do now is I want to see the average assessment value for residential versus commercial versus industrial versus agriculture, and also the coefficient of variation. So when I do this now, you see for different property classes and different sectors, I have a variability. And I can also say order by CV DESC for descending. So I want to start with the largest and go to the smallest. So vacant properties seem to have the largest variability. Now, they're not worth very much. The average assessment is 68,000, but they have a lot of variability within them, meaning the standard deviation is quite large compared to its average value. And if we scroll down through, you can see recreation actually has the lowest coefficient of variation, and agriculture, meaning most of the properties are similar to the actual average in terms of the magnitude of the average value of the property. So this is a great little mathematical formula that we put in here that helps us to look at sort of volatility within the data set. So maybe something will jump out at us as being kind of odd. For instance, forest and even recreation. Why are these so high? Why is there so much variability in proportion to their average in recreation and forest? So that's something we might want to explore. We're going to get into this later as we expand it more, but I just wanted to show you a general idea of numeric operations. So here are some of the mathematical things: addition and subtraction and cube root and absolute value. So all of these things are in here. And then there are these functions to get the absolute value, to get the ceiling of a number, to get the floor of a number, natural logarithms. So you look through here at rounding data, getting the square root of data. So we're going to actually do a lot of this later on as we begin to recreate formulas. Also generating random numbers, trigonometric functions. So all of these are inside of Postgres, just like you might see in something like Excel. And again, the difference compared to a GIS is we're formulating these functions right in the query. Let's look at this, just the CV again. How do we do that? Well, we'd have to first get the average. We'd have to first create a field. Then we'd have to calculate the average of a value and the standard deviation of a value, and then we'd have to calculate that and put it in the new field. So many steps in a GIS. With something like SQL, we just write it right inside the query. So this gives us a very quick look at some numeric operations, and what we'll do next is move to string-based operations.